Good afternoon, everyone. My name's Neil Singleton. I'm the Insurance Commissioner with the Motor Accident Insurance Commission, and I am chairing the session AI and Injury Claims. I'd like to start by acknowledging the traditional owners of the land on which we're all meeting across Australia and New Zealand, and pay my respects to elders past, present and emerging. If I can remind you, please, if you have questions during the presentation, put them in the chat function. At the end of Paul's presentation, I will run through the questions with Paul. Now, I'd just like to briefly introduce the presenter, Paul Beinat. Paul has been building AI systems since the early 1980s. He developed the Colossus knowledge-based system, and in 2004, the chairman of Allstate Insurance was quoted in the Wall Street Journal as saying that's worth $200 million a year to Allstate when referring to their use of Colossus. Paul is the co-founder of Eagle Eye Analytics, a US company where he acted as chief scientist. In 2015, US insurance companies voted it the best analytics company in the United States. So no small praise. Systems designed and built by Paul are in use in insurance companies around the world. And just by way of a sort of small circular story, when I first joined Suncorp in 1995, they were just introducing Colossus. So 26 years later on, get to hear from Paul on where things have got to since then. So thank you, Paul. Over to you.
Thank you, Neil. So my name's Paul Beinat, and even though it says insert company name down there, I'm actually from Finity. So before I start, I just want to talk about give some background to this, to say that the vast majority of statistical and machine learning methods use structured data expressed as vectors of data. Each data row is a vector, and all the vectors are the same length. In this case, the vectors can have non-numeric entries, but they can also be converted to strictly numeric vectors. That's why computer scientists refer to them as vectors. Vectors have very desirable properties. If we want to use these powerful methods, then we need to play the game. We need to stick with structured data. In this talk, we will examine how we can take advantage of human knowledge to turn unstructured text into structured data. And we'll see how this has the power to transform the performance of analytical models that can then have significant impact on claims handling. In these experiments, we have used adjusters' case notes as the source of our text mining activities. Case notes tend to contain information not found in the structured data about policies and claims. That's one of the key reasons why they write case notes, because the information in this note is relevant and not already present in the structured data. The other reason is that claims are often reassigned to another adjuster. So having notes is a key way for the new adjuster to familiarise themselves with the claim. But case notes are written by people in various styles and using various shorthand notation. They are inconsistent. They also contain misspelled words and terms, more so for medical terms. They can also contain subtle meaning, such as spinal surgery would not be efficacious. Sounds like something a doctor would say. We're going to look at two problems that we want to apply our particular text mining to. Both are US-based. One is auto bodily injury, what we would call CTP. The other is workers' compensation. For the workers' compensation problem, we are going to try to extract injury, treatment, and complications in medical terms. We also want to extract the drugs that are mentioned there. Our task was to develop a thing called a jumper claims model. Jumper claims are ones where the estimate reflects a small claim, but ultimately they become large claims. The criteria is pretty simple. It's where the estimate is less than $10,000, but the ultimate cost is more than $50,000. For the CTP application, we'll examine the description of the vehicle damage, including where on the vehicle the damage is. We will see where our injured party was within this vehicle. Again, we will also be extracting medical terms. Our task in this case is to identify severe claims. Similarly, these are where the ultimate cost is more than $50,000. Both of these models are based on the information available at fixed points in time. For the CTP problem, there are two times, once at 10 days and then at 60 days after first notice of loss. For the workers' compensation problem, it's 45 days after first notice of loss. Most text mining has traditionally been using a pipeline of processes. This includes things like removing superfluous words like the and a, stemming words, turning denying or denied into the common form deny, which are used to replace the original words. There are words reduction techniques. What is left is placed into what's traditionally been called a bag of words. This is a vector which is as long as all the possible words found. It's going to be very long. It is also going to be very sparse. 99.9% of all the entries are 0, with a 1 for any word found. For instance, we're using about 10,000 medical terms. This means that the vector would be 10,000 long just for medical terms. Imagine how many medical terms out of the 10,000 appear in any one claim. You can see just how sparse the ones are going to be. And that's just for medical terms. There are vector compression methods based on encoder-decoder neural networks. They can compress our long sparse vectors to a much shorter representation. The shorter vector is denser, but the information content is still sparse. Of course, this sort of approach doesn't handle negation, which will be important, and it can't represent phrases, which are going to be equally important. We're not interested in all the words, at least not for these projects. We want to find medical terms and drugs, and vehicle damage and claimant location. Let's focus on the workers' compensation work as an example because it uses more complete text processing. We have built a medical dictionary, as in the traditional sense, but instead of an explanation of the terms, we have encoded them with a severity. It's a simple 1 to 7 scheme, and assigning these is reasonably straightforward, especially if you have knowledge regarding traumatic medicine. The terms came from MESH, which stands for Medical Subject Headings, which represents lots of biomedical terms. We used only the terms related to injuries, their treatments, and medical complications. We also added synonyms. Things like spinal surgery is a synonym for laminectomy. They're the same thing. See, the phrase spinal surgery is a synonym of a single word. So any text mining we do has to be able to represent and process these sorts of disparate synonyms. We also built a dictionary of drugs. In this case, about 600 of them, along with their common and brand names, of which there are a lot more. We assigned these to a number of categories. So all the antidepressants were assigned to the antidepressants group, opioids to their own group, you get the picture. We can now, in theory, find all the medical terms in a case and get, say, the maximum severity we assign to any one of these. We can also find all the drugs being taken and add them up by drug category. This takes thousands of medical terms and drugs down to a few pieces of structured data that can be added to the traditional policy and claims information. I skipped a bit though, an important bit. Claims people are not going to type reliably. They can be time poor and don't necessarily even know how to spell some medical terms. So hematoma, H-A-E-M-A-T-O-M-A, and hematoma are obviously the same thing. Same for laminectomy and lamenectomy. The second's obviously a misspelling of the first. We don't want to lose all the words that are misspelled in some way, naively thinking that they're different words. To address this, we've implemented a soft text matching algorithm based on the reliable Yarrow-Winkler, which I'm sure many of you will be familiar. This returns the degree of match between two words. Ordinary words, though. Of course, it needs some modification in order to match medical terms, which it was not designed to do. For instance, it thinks that heed, H-E-E-D, and head is a good match. You can see the problem. We modified it so that it could do two things. Firstly, match medical words reliably and not confuse them with ordinary words. And secondly, that it can match phrases because some terms are going to be phrases. Finally, we have to be able to detect negation. Otherwise, it will falsely assume that the medical term exists on the case when it really doesn't. The term denies having asthma was actually found on a real claim note. You can see that if you thought this case involved asthma, then you would be mistaken. To address this, we developed a series of negation templates because there are many ways of specifying negation in English. These are external to our Yarrow-Winkler type text matcher, of course. Have we got them all? Well, of course not. Finally, we need to talk about modelling and methodology. Up to this point, everything that I've described is an unsupervised algorithm. In other words, there's no dependent variable here. We're just trying to understand and use human knowledge to reliably match text to a knowledge structure that we have involving medicine and drugs. On the supervised end, the model that was used for both projects is a multiplicative boosting ensemble of custom developed trees. The tree algorithm was specifically developed for use on insurance data. So it understands, it's designed to make better decisions on skewed distributions found in insurance. The ensemble is multiplicative, whereas all the others are additive, in the same way as log-linked GLMs produce multiplicative relativities because it cannot produce a negative result. With the advent of arbitrarily complex models, good methodology is imperative, and ensembles can be very complex. How complex? Well, Google's DeepMind have fitted models with hundreds of billions of parameters, the famous AlphaFold deep neural network that can predict how proteins will fold. We can have so many parameters that any system can essentially memorize the data, at least in theory. While this sounds impressive, it can struggle to generalize well on unseen data. The performance of any analytical system is not how well it performs on the data used to train it. It's how well it performs on data it's never seen before, because using it prospectively is where the value is. In both of these projects, we have set aside data as holdout data sets. This data would not be used to train the system, but only to test it after training. This is the gold standard. The slides that follow are the performance of the trained systems on the holdout samples. The first one is the CTP example, or bodily injury claims. As it says, a severe claim is one that ultimately settles for more than $50,000. Of course, there aren't very many of these, a little less than 5% of all claims, but just as well in order to keep the thing affordable in terms of premiums. At 10 days, the model finds a lot more severe claims than the insurance company does, about 4 times as many again. This means that the insurer can make claims assignment decisions very early in the life cycle, presumably assigning severe cases to better handlers. You can see that at 60 days, the insurer can identify more severe claims than at 10 days, unsurprisingly, of course. What makes this difference is that there's a lot more information about the injuries and perhaps even their treatment than would have been known at 10 days. At 60 days, the system plus the adjusters can identify almost 80% of all the severe claims. At 60 days, the system finds about 1.5 times as many severe claims as the handlers do. Why doesn't the model find all the ultimately severe claims? The answer is, of course, that it's not possible. Severe claims can develop from unexpected beginnings. This could be because the medical treatment doesn't resolve the injuries suffered in the accident. The person is perhaps left with some disability. Perhaps the injured person already had some disability. It could be that some unforeseen medical complications occurred, for instance, an initially undiagnosed ligament injury. It's the variance of the medical journey that's one of the causes. Another cause can be that we haven't extracted all the relevant terms from the data, or perhaps, more likely, is that there was no data to extract for some claims. It just wasn't there. Regardless, the system still does better than the claims handlers at identifying large claims. The insurance company that this was done for has used the system to allocate claims based on severity, matching it to adjuster suitability. They think that this matches severe claims to better adjusters and reduces claims reassignments significantly. They think that this has reduced their claims handling expense by over 3%. That's why they use it and are still using it. This is the workers' compensation project that mined the text from the adjuster's notes. All the known large claims have been removed already. What we have here are what they think are small claims at 45 days after first notice of loss. In there, they know there are a number of jumper claims. Recall that a jumper claim is one where the incurred at this time is less than $10,000, but the ultimate is more than $50,000. Actually, the average is more than $100,000. We were looking for medical and drug information in claims at this point in the claim life. The graph shows the model spread. The model outputs the probability that a claim is a jumper claim. In this case, the graph shows the average incurred loss at 45 days and the ultimate for the claims accumulated by probability in bands. Remembering that this is holdout performance, in the top 5% of probabilities, that's the left-hand bands produced by the model, there are more than 30% of all the jumper claims. In the top 15% of the model, that's the top 2 bands, contains more than 60% of all jumper claims. You can see that the incurred, paid plus estimate, in the leftmost band is far lower than the ultimate incurred. The expectation here does not match the ultimate performance and by a wide margin. At the other end of the model, on the right-hand side, there are no jumper claims at all. The incurred at 45 days is higher than the ultimate cost. These claims warrant minimal attention. As someone said to me at one stage from an insurance company, we could just get the cat to settle these claims. The organisation that this data came from was a workers' compensation state fund representing a whole US state. This state has implemented this model and changed their claims assignment practices as well as work allocation. They state that they've seen a 4% reduction in actual paid claims that closed 2 years after this implementation. A number of other US states have also implemented a jumper claims model and re-engineered their work practices. You can see that finding jumper claims is a different and more challenging problem than to find large claims. Within the case notes, there is valuable information that relates to this problem. Of course, that information was always there and always available to adjusters. They just miss the implication of it. That's all. That's all that's going on here. Regarding the training of the jumper claims model, the training data size was about 18,000 closed claims, workers' comp claims in this case. As you can see, the dictionary-based text mining found around 40,000 medical terms and 3,000 drugs. The most often used drug categories were analgesics, opioids, and antidepressants. I don't think anyone would be surprised by this. Perhaps more surprising is how many had multiple drugs in different categories even. That's a lot of information that had not been used before, and all of it relevant information. Did we find everything? It did appear that in claims where we found nothing, that there appeared to be nothing to find. We didn't look at the claims where we did find things if we actually found everything, because that's a very, very difficult task and very time-consuming task. But had we found more things there, maybe it may have changed the outcome. However, without this medical and drug information, both models' performance was almost catastrophically poorer. So what has really happened here? Most machine learning algorithms are actually quite dumb. The most often used induction trees, like CART, are nothing much, and even artificial neurons themselves are simplistic. The complex behavior and consequent performance comes from combining many such simple concepts into a coherent collection. The other thing that brings improved performance is the capacity of the feature space and its correlation to the data. The better the features, the better the performance. In our case, the features that we added have come from human theory, as embodied in the drug and medical dictionaries. It's human knowledge that has allowed us to create such powerful features that transform the performance of the resultant systems. Human knowledge is a very underutilized resource in machine learning. There's no doubt that mining textual information using these types of technical dictionaries can extract very useful information, critical to creating models that exhibit powerful performance. These models have been used to transform claims practices now in multiple US jurisdictions. This text mining that we've been describing here now runs in real time, and it is scanning claims every night in multiple places in the United States. There are other opportunities for making these models even better. Case notes are not just a repository of medical terms and drug references. There's other valuable information that's unrelated to any medical circumstances. You can see an example here now. It's not an uncommon circumstances. These two actual notes are associated with a claim where a worker fell from a ladder, a normal step ladder. The medical evidence was that there were no substantial injuries. Within the notes was the fact that he was taking methadone, normally a drug associated with heroin withdrawal. Naturally, this was a jumper claim, and it was identified as such by the previous model. But there were other clues here, and these could be more relevant where the medical information is not equivocal. Case notes can be regarded as a sequence of events. Some sequences will be predictive of a problem with a claim. This sequence, apart from the methadone, is also indicative of a potential problem with a claim. Of course, this type of text mining requires more than technical dictionaries. We need to develop a way of classifying case notes as containing types of behaviours. Called, no answer, called, no answer again. If we do this, then these can be mined using other techniques, behaviour pattern mining. Similarly, this could add power to the feature space, adding different theory uncorrelated to the medical and drug data currently processed. Now, machine learning is traditionally focused on producing powerful algorithms. We are all familiar with GBM and XGBoost. They produce impressive results. There are two main ways of incorporating human knowledge in these algorithms. One is by limiting or augmenting what conclusions they can make. In other words, changing the induction tree inside it by forcing it to make certain conclusions or forcing it not to be able to make certain conclusions with human theory. But another way is to augment the feature space. Here we have chosen the latter approach. Human knowledge is a very underutilized resource in machine learning, I think. Thank you for your kind attention. I hope you found this interesting. And if you have questions, I'll be very pleased to answer them, if I can.
Thank you, Paul. That was fascinating. And if I can just remind everyone, please, if you have questions, please put them into the chat. We've got a couple there already. But if I can have a liberty, please, and just jump in with a question first. Paul, early on this morning, Estelle Pearson spoke about some of the, what she saw, some of the future trends. She spoke about measuring sentiment in conversations. Do you see AI measuring sentiment in conversations?
I think certainly we are on the space of doing that. Some time ago, there was a system called Albert. It was a derivative of a system called BERT. BERT is a very deep neural network that basically learns languages. It had at that stage 400 million parameters that it could tune. And you could actually train it further on some data that you had, where you could, for instance, have sentences of information and then sentiments assigned to them. And it could learn to classify the different sentiments based on the structure of the sentences that you had in the training data. So it's certainly possible to do this right now. And that's actually, compared to some of the problems that people are attempting to attack now, I think that's a very, very tractable problem, and people understand it enough now and have produced enough intellectual capacity in neural networks to be able to answer some of those problems, yes.
I can certainly see a lot of benefit from that, and perhaps whether they're jumpers or some other mental health issue, being able to just understand the sentiment of a conversation can be very powerful.
Oh, yes. And in our case, because we've been limited to case notes, we've attempted to get the mental health aspect out of it by looking at people who, and the types of drugs they're actually taking, whether they're taking antidepressants, anti-anxiety drugs, things like that. If you've got a workers' comp claim and you're starting to take those drugs, then you start to know that that's going to be an issue in that workers' comp claim too. You don't know how bad, but then you're into sentiment to figuring out if you can find out if it's worse or not. Yeah.
Okay, now if I just turn to some of the questions that are coming through, sorry, taking you back to one of your slides, Ray has asked, in terms of the chart you showed, what was the x-axis referring to?
Let me go back. Is it this one?
On the jumper.
Yep. So this is based on the probability of claims occurring. So the two end bands contain 5% each. The bands on the left, and the blue and red one on the left and the blue and red one on the right, just contain 5% of the claims. And the next inner ones contain 10% each. And the next inner ones contain 20%, and the next ones contain 25%. So it's kind of it's a little bit like a normal distribution. So the ends are sparse. They're only 5% each. But you can see the whole idea is to get as many jumper claims as we can into the left-hand band. So in this case, by looking at 5% of the claims caught by this system, they'll actually have 30% of all their jumper claims in there. And they actually took up 15% of their claims out of this and assigned them to more experienced adjusters in order that they would get 60% of all the jumper claims in there. And they think by doing that, well, these people are convinced by doing that they've saved 4% of claims cost over a 2-year period following the implementation of this system. They've also got a system in front of this, which is like the previous one that looks at severity. And so if a claim is outright severe at, say, day 10, then they would take that out and assign it to better handlers, right? And then after this, at 45 days, they then look at this jumper claim model and see whether the stuff that's left out that isn't overtly severe, they can actually then, in a more sophisticated way, assign the better ones, the more difficult ones, the ones that are going to jump potentially to different handlers.
This feeds into the next question from Thorough around the what were the operational changes that were made to achieve that 4% reduction? And is it simply the reallocation or reassignment of the case, or are you aware of any other operational changes that were made?
The only thing that they're telling us is they've operationalized the severity model and the jumper claim model. And it's really just matching. They think that the difference is being able to match the sophistication of the claim with the capability of the claims handler,
right? Essentially.
Okay. And this has been replicated, in other US states that have, because this became the prototype, of course, right? And so other US states are now doing this very same thing.
And I guess that's the operational side of things, but in terms of the data itself, have you seen any of the insurers change the breadth of the data or the type of data they're capturing to inform the model?
So this model's been redeveloped a number of times since, and yes, some of the organisations here have attempted to extract more information that they're still putting in claim notes, but they've had an imperative amongst their adjusters to extract more relevant medical information from talking to the doctors who are treating some of these people. Because it's workers' comp, you're allowed to talk to those doctors, right? This is very different from auto liability. But I certainly know that they're doing that. But I haven't been involved in this for 3 years or more now.
I know from most of the actuaries I talk to, there's never enough data in the world. There's always something more you can capture. Oh, yeah. A question from Timothy. In terms, and this is a long question, I'm afraid. Do you see the major human interventions and overrides happening at the data manipulation stage within the algorithm adopted or post-model output?
So the manipulations that we do are really simple. We're just augmenting feature space, right? We've just got this really complicated process with dictionaries and soft matching and all that stuff to essentially augment structured data with a few more things. They're very powerful things that we're augmenting the data with, and they lead to models like this. But these things can be far more subtle in some ways. Lots of unsupervised methods can be used to transform feature spaces into potentially more useful representations. As an example, some more sophisticated clustering algorithms can transform feature spaces and add new information besides the overt variables that we're all familiar with by adding grouping information to these. Sometimes this grouping information becomes very valuable in terms of the impact that it can have on the models that we produce. Other things that that I've been involved with, I've done some work more recently that I haven't actually used yet in this case, looking at the geodesic distance of data. Because data doesn't really, even though we think data exists in a kind of a multi-dimensional cloud, that's really not the case. That's just our limited ability to understand data. Data actually exists on a much more convoluted and complex manifold. We just think of it as a cloud. And things such as PCA then make that look much more like a cloud than it really is, and give us a very false sense of understanding of what the data is really about, I think. I hope that's answered that question.
I'm sure Tim will follow up if there was another aspect to that. Paul, one of the things that sort of talk about a lot, we hear about a lot, algorithmic development, deep learning. While all of that's going on, where have you been at, or where do you see things progressing?
I think there have certainly been some great advances in deep learning. The great advance in deep learning is processing image information, and convolutional networks and things like that have been fantastic at doing this type of task. So much so that people have made many applications of these things, and then people started to discover that the image processing was brittle, and then we've had new theories about having things compete, change the image and have the thing misclassified, and then make new training data, redevelop the thing, adversarial learning, in other words. We don't tend to use this very much in insurance at all. We've done work in the past on artificial neural networks, not very deep ones, by developing different types of back propagation algorithms. Probably most people may not be aware that the back propagation algorithm assumes Gaussian distribution of errors, and obviously most of our data is nowhere near that. So we managed to reconstruct back propagation algorithms for the gamma error structure and for the Poisson error structure and things like that. And it turns out that those types of neural networks can model data far more effectively than say GLMs, which are the kind of standard that a lot of people use. But deep networks, deep networks are actually a fantastic thing. Since the early work of Geoffrey Hinton, who discovered how to solve the problem of correlation of layers in networks, they've been an actual boon. Lots of people doing stuff. We just don't use them much, right? Because we don't understand them much, and there's so many different types of layers that people implement inside of these different networks, from attention layers to invariance layers. So it's become a field unto itself these days. One day we'll start using this stuff, I think. I hope.
Okay. No, look, thank you, Paul. Look, I'm sure the audience will follow you up with further questions or to explore this in more detail. I think on any level, understanding the claims management allocation models, cost control are fundamental to scheme health. So thank you for your presentation. Thank you to the audience for their questions. Wish everyone the best for the afternoon.
If anyone has questions, you can always email me. Yes, I'll be very happy to have.